Hello everyone, welcome to lecture number 60 and the final lecture in this NPTEL course on Riemannian geometry. So I thought that I'm essentially done with everything I wanted to talk about. So I thought maybe I'll end with a very nice theorem due to Schur, since we have spent some time in the last few lectures talking about constant sectional curvature, constant Ricci curvature and so on. So I thought this is a good way to end the course. So let's recall that we say that the sectional curvature is a constant if for all p in M and for all two planes in the tangent space to M at p, the sectional curvature of this two plane is equal to kappa. Okay. So here kappa is just some real number. Okay. Similarly, in the previous lecture I did not make a formal definition, but I sort of touched upon this point that we say that the Ricci curvature is a constant, let us say lambda, where lambda is again some real number, if for all points in M and for all tangent vectors at that point, the Ricci curvature of V comma V is equal to lambda norm V squared. Okay. Or this is actually equivalent to the statement that the Ricci curvature of U comma V is actually equal to lambda times the inner product of U comma V, where U and V are arbitrary tangent vectors at P. Okay. So in this case we also call say that the manifold Mg is an Einstein manifold. Okay. That is because this equation that the Ricci curvature is equal to lambda times G, this sort of shows up in Einstein's equations in general theory of relativity. Okay. So in honor of Einstein, these such manifolds, such Riemannian manifolds are called Einstein manifolds. All right. So natural question is, what if this kappa and lambda are allowed to be functions of the points, are allowed to be functions on M instead of just constants. So that means in the case of sectional curvature, suppose so that is, what if we allow the sectional curvature at a point P to be equal to kappa of P for all two planes at that point. Okay. So with respect to the two planes, it is a constant function, but that constant is allowed to vary from point to point. Okay. Similarly, what if the Ricci curvature is allowed to be this for all tangent vectors? Okay. So again, for different tangent vectors you get different answers, but at a given point it only depends on that point. Okay. But as the point varies, this number is allowed to vary. What happens if you sort of relax your definition of constant scalar curvature to this sort of pointwise constancy. It turns out, and this is the theorem that I want to prove, that this is actually equivalent to having constant sectional or Ricci curvatures. So this is something quite remarkable, that even if you allow these constants to vary depending on the point that you are looking at, it turns out that they will actually not vary at all, they will be constants. Okay, so this is the famous theorem of Schur. So I will write it as two propositions and then prove both of them. So the first proposition is Schur's theorem for sectional curvature. Okay. So what this says is that if n is bigger than or equal to 3, so this is key, this is not true in dimension 2. So if n is bigger than or equal to 3, the following are equivalent. 1, the sectional curvature is identically equal to 2 kappa. Second, there exists a function, let me denote it by k, such that for all p in M and for all two planes in the tangent space at that point, the sectional curvature of the two plane is given by k of p. So it is independent of the two plane that you consider, but it depends on the point that you are looking at. Okay, it turns out that this is actually equivalent to having constant sectional curvature. Surprising, right? It's similarly, we have Schur's theorem for Ricci curvature. Again, it's similar in spirit. So the following are equivalent. So one, that the Ricci curvature is a constant, which means it's an Einstein manifold. And second, there exists a function f such that the Ricci curvature at p is equal to f of p times the metric at p. Okay, so again this is some sort of pointwise constancy of the Ricci curvature, that it is independent of the tangent vector, but it depends on the point. But it turns out that this is actually equivalent to the Einstein condition. Okay, so let me first prove that in fact the Ricci curvature, Schur's theorem, actually implies the one for sectional curvature. So proposition 2 implies proposition 1. Okay, so obviously 1 implies 2 is trivial. You can just take this function k to be a constant, right? So obviously 1 implies 2. Why does 2 implies 1? Why does 2 imply 1? So recall, I think this must have been in lecture 24 or 25, that we proved this a while back, that the sectional curvature actually determines the curvature tensor. So recall that if the sectional curvature at the point P is identically equal to k of P, so if the sectional curvature at P for any two plane is actually equal to k of P, then this implies that the curvature tensor at that point has an explicit formula. So this is simply given by this number k of P times xp wp multiplied by yp zp minus xp zp multiplied by yp wp. Okay. So in other words, in components, if you take r, I, j, k, l at this point P, then this is just going to be k of P times GIL GJK minus rather, yeah, let me not do it in components, let me just take an orthonormal frame, implies if this is an orthonormal frame such that E1 is some given vector xp, orthonormal frame for the tangent space at P, then what is the Ricci curvature of x comma x? By definition, this is the summation I going from 1 to n of EI, sorry, little EI, XP, XP, EI. So again, if you take I equals 1, then the curvature term is going to be 0. So this is going to be the summation I going from 2 to n of Rm EI XP XP EI. But then by this formula, this is the same as k of p times summation I going from 2 to n of EI EI times XP XP minus EI XP times EI XP. Right, but because this is an orthonormal frame, these two are going to be 0 and this is going to be 1, this is going to be 1 or also norm xp squared, right. Okay, so you basically have you basically have k of p times summation I going from 2 to n of norm xp squared. There are n minus 1 terms, so this is simply n minus 1 times k of p. So that means that the Ricci curvature at P is simply n minus 1 k of P times the metric at P. Okay. So now just apply proposition 2 with this as your function f. Okay. Then by proposition 2, this function f is actually identically a constant. Okay. So but then this implies that that this function k is identically n minus 1 times lambda. So just take this to be your kappa. So that means that the sectional curvature is constant kappa. Okay. So clearly proposition 2 implies proposition 1. So now how do you prove proposition 2? So the key point is the following lemma. So this is called the contracted Bianchi, contracted differential Bianchi. Okay. What this says is that if you take the divergence of the Ricci curvature, which is defined to be precisely this, okay. So by definition this is this is simply G upper JL. You take the covariant derivative of the Ricci curvature in and take the jkth component of that, and then raise the index using the metric. Okay, so this is the definition of this. then the claim is that this is equal to half times the gradient of the scalar curvature. So this is the scalar curvature. Okay. So let's prove this. So the proof uses the differential Bianchi. So let me remind you of what the differential Bianchi was. So the differential Bianchi was that if you take right, that's and then cycle through maybe the first two or the last two indices. So let me cycle through the last two here. Then this is you basically take the covariant derivative with respect to L of R I J M K plus the covariant derivative with respect to K of R I J L M. Then that is 0. Okay. So I am going to use this differential Bianchi identity. Okay. So we compute at a point P using normal coordinates. So what this means is that Gij at P is delta Ij, and the derivatives, or in particular the Christoffel symbols, they all vanish. Okay. So in normal coordinates the differential Bianchi is the following. So the differential Bianchi implies that if you take the usual mth derivative, so all of this is at P, right, plus del L R I J M K plus del K R I J L M, all of this at P, this is equal to 0. Okay. So now let's use this. So what do I want to compute? I want to compute this, right, where you are now summing over J, but because you are working with normal coordinates, this is the same as the usual derivative of Rjk in the jth direction, right, but that's the same. I mean Rjk, the Ricci curvature is defined by tracing over, let's say, the first and the fourth element. So this is Rijki, where you are now also summing over the repeated index I. Okay. So by the Bianchi identity, so I am going to apply again the Bianchi identity, differential Bianchi, to the final two entries. So by that this is going to be minus del I R I J J K minus del K R I J I J. Okay. All right. So so now if you look at the first term, so that's forget about the minus sign. So that's del I R I J J K. So you are basically summing over the second and the third index. So that gives you a Ricci curvature term. So this is basically just going to be del I Ricci curvature of Ik, which again we are using normal coordinates. So this is actually just the divergence of this, which again, I mean, I is just an index. So this is the same as this. Okay, because I is just a dummy variable, right, it is just an index. Okay, so that means that the first term is basically minus the same thing that appears on the left. How about the second term? So the second term is del k r ij. So that is the same by the symmetry of the curvature tensor, that is the same as del k of r. I am going to now flip these two around, okay. So that is the same as I j j I. So now again you are summing over the second and the third, and you are summing over the first and the fourth. So you are doing two traces, right, you are computing two traces. When you compute the first trace, maybe sum over the first and the fourth index, you get the Ricci curvature. When you take a further trace, you get the scalar curvature. So that is just going to be minus del k of the scalar curvature, or that is the same as minus the covariant derivative. I mean, the covariant derivative of functions and regular derivatives are the same, right. Okay, so the upshot is that you get the following. You get that the divergence of the Ricci curvature is equal to minus the divergence of the Ricci curvature minus the derivative of the scalar curvature, which means that twice the divergence of the Ricci curvature is there is a minus sign here, there is another minus sign here, so you will get plus. So this tells you that the divergence of the Ricci curvature is half the derivative of the scalar curvature. Okay, so this proves the contracted Bianchi identity. So now how do you prove the proposition from here? So again 1 implies 2 is trivial. So the key is to prove that 2 implies 1. Okay, so suppose there exists a smooth function such that the Ricci curvature at a point P is f of P times the metric G of P. So now if you trace this symmetric bilinear form, so that means that the scalar curvature, which is equal to the trace of the Ricci curvature, or let me maybe write it in the form of orthonormal basis. So if E1 up to En is an orthonormal basis for TPM, then the Ricci curvature of EI comma EI is just f of P, okay. So which means that the scalar curvature at P, by definition this is the sum from 1 to n of the Ricci curvature of EI comma EI. This is just going to be n times f of P. So as a function, the scalar curvature is basically n times f. We get this important relationship, right. Okay, so now or in other words f is actually s divided by n. Okay, so now let us apply the contracted Bianchi. So the LHS of the contracted Bianchi is what? It is the divergence of the Ricci curvature, but by our hypothesis this is f times the metric. Now the metric is a covariant constant, right. So that is just going to be GJK times nabla upper J applied to f. But what is nabla upper, what is f? F is s by n. So this is going to be GJK by n times upper J applied to s, which is the same as the usual kth derivative. So you can use the metric to lower the index divided by n. Okay. But what is the RHS? Sorry, I should have yeah. So the RHS is this divided by 2, right. So that means that n minus 1 by 2 is 0 for all k. Okay. But if n is bigger than or equal to 3, this implies that n minus half is obviously not equal to 0. So this means that the gradient of or the derivative of s should be 0 for all k and at all points. So but then because our manifolds are always connected, this implies that s is a constant. But s was basically given by n times f, so this implies that f is a constant. Okay, which implies that that the Ricci curvature is some constant times the metric, which implies that 1 is satisfied. Okay, so this completes the proof of Schur's lemma for or Schur's theorem for the Ricci curvature. All right, so that's it for the course. I hope you have enjoyed and also learnt a little bit, and yeah, I mean most importantly, hopefully you have gotten a flavor for what modern Riemannian geometry looks like. I'm sure the course must have been not very easy, but that's because I decided upfront that I will not. I mean, I wanted to keep the course at a certain level so that you at least get some flavor of what it is to do Riemannian geometry in today's times. I mean, even having said that, I mean most of what we covered was basically Riemannian geometry already known by maybe the 1960s, but even so, at least the language is still and some of the techniques that we introduced are still used. So hopefully going forward you might be able to take your lessons from this course and take up more advanced topics in Riemannian geometry and geometric analysis, right. So take up topics that are more relevant for the kind of research that is being done today. All right, so thanks once again. It's been a pleasure to give this series of lectures. Thanks.